I will discuss existence of normal subgroups, so the continuation of the question from this morning. So I have in mind to find normal subgroups in Tame K2 or Tame K3. But first, I'm going to describe a general machinery to produce normal subgroups in a given group, any group. So it's a small constellation theory. So first, recall the definition of delta hyperbolic space or Gromov hyperbolic space. So geodesic metric space X is delta hyperbolic. Delta is greater or equal than 0. If all triangles in X are delta thin, and delta thin means that for X, Y, Z in X, so it's a geodesic, so you have segment between X, Y, and Z. And you look at the union of the segment X, Y, and Y, Z. You look at the delta neighborhood of that, and it should contain the third one. So in the classical picture is that if you do X, Y, and Y, Z, it should contain the, is that right? Yeah, X, Z, yeah. So it has to be for a uniform delta. Yeah, you have a delta which is okay for everything, and for instance, for the simplicial tree we encountered this morning, a tree is by definition, a tree is zero hyperbolic. So simplicial tree is zero hyperbolic. Okay, and now I have following a black box, that's a small constellation theorem. So it's by Damani, Girardel, Austin, and I guess it was published around 17. So let G be a group acting by isometry on such a space. And I guess you want the action to be non-elementary. So here it means that there is no fixed point in X or at the boundary. So it's not a kind of a trivial case. And assume there is G in the group. So 2 words I have to define. So it is loxodromic and with a WPD property. So loxodromic. WPD. So weakly, proper, discontinuous. I will explain just after the definition. So if you have such an element, then there exists n0. So for any larger integer, any n larger than n0.
Sorry.
Yeah?
I want to follow. So what's WPD?
Yeah, just after, definition just after. So for any n larger than n0, you look at the n iterate of G. You look at the smallest normal subgroups containing this element. So that's my notation for smallest normal subgroup. So the normal subgroup generated by this element. So if you want, it's the intersection of all normal subgroups containing Gn. And the result is that this group, so for sure it's normal in a G, it contains only loxodromic elements. So loxodromic elements, they act by translation on an axis. Maybe you have to say quasi-axis or something, but there is a translation length, and the translation length of all elements, so everybody is loxodromic except the identity, and the translation length is more than G to the L. So containing only loxodromic elements, so except identity, with large translation length. So in particular, G is not here, so in particular, this is really not equal. So that's a way to produce some proper normal subgroups in your G. Okay, so I'm going to use that as a black box. Like, if I have an action on a delta hyperbolic space, for instance, a tree, if I'm able to find a loxodromic isometry with this property I'm going to define, then I have a normal subgroup. Okay, so good. So WPD. So let me give you the first. So it's a lot of quantifiers. So I give the definition. After that, I do the picture. So for any point in your space, for any radius R, there exists M. If I look at the set of elements in the group that almost fix up to R the 2 points x0 and G to the M x0. So by definition, this is the element H in the group such that the distance between x0 and hx0 is less than R, and also the distance between gmx0 and h, gmx0 is also small. You want that to be finite. Okay, that's the definition. For any points, any radius R, there exists M sufficiently large. In fact, yeah, in fact, it works for. This is finite. So picture. So when you have so that's G inside G acting on X is WPD if that. Okay. So the picture is you have your axis. So G should be loxodromic first. Yeah. So a first remark is that, so this is a formal definition, but then you look at the definition, you work a little with that. First lemma is that you can replace the for all by here exists. So if there exists x not, in fact, the same as for all. So here you can put there exists, and since it's equivalent, I'm going to choose x0 to be on the axis. It's easier to the picture. Okay, so I choose a radius R. Now I take M sufficiently large. So large means that the distance between x0 and gm x0 is large with respect to the radius. So again, I have this ball of radius R. And I look at the h that moves a little x0. So h x0 is here. And simultaneously, h of this point should be here. So this point almost fixed this point and this point up to your R. So I accept that there are a few of them, but finitely many. Okay. So if you have this property, then you have a proper normal subgroup. Yeah. What is what? The axis. So it's when you have an isometry on a delta hyperbolic space, you should think like it's a classification analogous to to the classical hyperbolic plane, where your isometry are elliptic, parabolic, or loxodromic. And elliptic, you have a fixed point or a bounded orbit. And then you could have a fixed point at infinity, or you have two fixed points at infinity. One is attracting, the other one repelling. And then you have a kind of axis between these two. So my map is loxodromic. So I have two fixed points at infinity, and I have an axis. So for the tree, it's really going to be an axis. In full generality, maybe it's a quasi-axis. So you have such a picture. WPD is for weakly properly discontinuous. Not my invention. Yeah.
So you can pick x0 anywhere, not on the axis.
Yeah, that's an exercise to see that it's the same. Yeah. And in fact, we're going to apply it for the case of a tree. So for a tree, it's even simpler. So let me give you the version for the tree. In fact, on a simplicial tree, it's important to have simplicial. So in fact, on a simplicial tree, so if X is a simplicial tree, G antigon X is WPD if, in fact, so again, G acting as a loxodromic isometry on your tree, so you have an axis. So you want to find 2 points on the axis, so there exists UV on the axis of G, such that the true stabilizer, the stabilizer of U and V is finite. So you can remove the radius R, the error. You just look at the group fixing U and V. If it is finite, it's WP. I should comment that we say that G is WPD, but in fact it's G inside the big group G. So if the big group G is important in the definition, it appears in my definition of the fixator. You see, if I enlarge the ambient group G, maybe my fixator could be bigger. Maybe it could go from finite to infinite. So you should think, well, for instance, if you look at the action of SL2Z on the hyperbolic disk, so for instance, that's a baby example where you have an action on a hyperbolic space. Any loxodromic element here acts as a WPD element, but if you replace Z by R, none act as a WPD element, because so by changing the group and not changing the element, change something. So be careful that it's really a property of the element with respect to the ambient group. Okay, so.
So the definition you asked that X0 is in the axis?
It does not matter. So for the picture, I put X not on the axis, but in the definition is for all. But I mentioned that for all is equivalent to existence of 1. So you just have to check. If you check it on the axis, it's OK. It's an exercise. It's a true exercise. It's five lines proof.
So what is fix UV?
What is what?
Fix UV?
Yeah. So it's the group. Yeah, it's a subgroup fixing U and V. All elements in G. So that's the H in G, such that H of U is U, H of V is V. No trap here. Okay. And theorem. Pick any anon map, say Y, YD plus X is a WPD element for the action of Tame K2 on the base set tree. And okay, so I guess over any field except if D is P and you want characteristic P, then you just have to change the D in another one and it's okay. No, so you have to avoid where D should not be a power of the characteristic, but otherwise it's really, for any field it's okay. And the proof is that I can understand the stabilizer of 2 points on the base-set tree. In fact, if you take U and V at distance more than 6, the fixator is finite. That's it. So it's easy. It's an easy computation. So there was this question this morning of Laura about attribution. Okay. So here, in fact, I say that the group, so consequence, the group S Tame K2 contains a lot of normal subgroups, many normal. Okay, so it's not a simple group. So I guess the first appearance of this result was probably in '74 by Danilov. So that's a long time ago for Gabriel. It's a geological time. It's the year I was born. I mean, sorry. So in fact, it was completely. It's a 4-page note. It was completely forgotten. And after that, we work on the problem with Jean-Philippe Furter. And so we work on this problem. Around 2007, I guess. So we didn't know the paper by Danilov. So we found the paper of Danilov when the work was done. So it was a little disappointing. So we have a variant of this argument. We rediscovered this result. So it was using some old small cancellation theory. So okay, it was disappointing, but then it was useful to me to have done this proof again, because then I was able to help Serge to sort out the small cancellation stuff for replacing hot by beer. So here it's not a tree anymore, it's an infinite dimensional version of the H2. So okay, but we have the same, we use the same statement. But this was published in 2013. And still the black box was not really available at the time. So after that, my PhD student Anne Lonjou, she had access to the black box as a preprint, and so she gave maybe a more neat version, because there was some assumption on the base field, and she did for any field using the black box, and so simplified the argument. And then again, with Anne, we looked at the black box, which is 100 pages. It's hard to understand. So we try to rewrite a proof in the case of a tree, just to try to understand. So we have a paper which is called an introduction to the small cancellation theorem, just focusing on the case of tree. And you can find this statement here. But I guess. Mine is 5 pages. 5 pages, but it's 5 is not 5 lines. Yeah, so it's not so easy. Yep. Okay, so let's do dimension 3 now. So n equals 3. Remember, I have my simplicial complex for any number of variables. So for 3 variables, I have a triangle complex. It's dimension 2. And let me make a picture here. I would like to keep the picture. Okay, so yeah.
So you have examples of normal subgroups. You have this very big one, Jacobian
Well, at least the quotient cannot be finite. The quotient cannot be abelian. So you have constraints like that. So because I work over algebraically closed field, and if you're working over R over a perfect field, that's a talk of Julia, which she said, I can go to Z mod 2. So it's finite and abelian, but it was not. It was over a perfect field, which is not closed. But over C, which is probably your favorite one, no. Yeah, no. So no, for over C, there is no meaningful quotient. It's yeah. Okay, so Tame case free acting on a triangle complex. So I just want to put a few vertices. Again, as in the case of the, so I have my personal code for the type of vertices. So that's for type 3, and then I have types 2 and types 1. So let's do it. So here I have x, z. And I'm going to put z. Okay. So here it's y, here it's x, here it's xy, here it's yz. Okay, I don't put the bracket anymore, but here it means the class of the identity. So it's my g1, g2, g3. It should be like that. No? Class of that, but I don't put the class anymore. So this is my vertex. This vertex of type 3 is linked to this vertex of type 2 with x of z. X of z are part of the coordinate, and z is one of the coordinates. So I have here already 6 triangles. So I guess the standard one is to take x, and then xy, and then xyz. So that was my definition. But xyz, up to affine automorphism, you can reverse the order, so you get the 6 other one. And then I'm going to put another one. So here, something like that. Here I can put x, y, z plus any polynomial in yz, in xy. I can do the same on the other side. So here I do x plus a polynomial just depending on y, x. And then I can do the triangular one when I put q and p at the same time. So it's going to be here. So x plus q of y, z plus p of yz. And then it's an exercise to see that really it's linked like that, and you have picture. So that's a few of the triangles in my triangle complex, just to give you a feeling of the space. Okay. So the first result, so let me call C the complex. So the complex C of Tame K3 is simply connected. And here, I have to assume characteristic is 0. Okay, so it's dimension 3. It's also now for all the results, I need to make this assumption. Why do I need this assumption? It's because I'm using it's just a reformulation of the result I mentioned this morning of Chestakov and Mebaev, who proved that Tame K3 is not the full automorphism group. In fact, it's really their proof I use to prove that it's simply connected. So just a one-line idea of proof. Use Chestakov, Mebaev theory of reduction, Mebaev. Okay, so what do they prove is that so first you can prove that when you have a two-dimensional graph like that, a two-dimensional complex, it's interesting to look at the link of a given vertex. So the link means you look at all vertices at distance 1, and you put an edge when they are in the same triangle. So here you see an hexagon in the link of this vertex. So the link is a graph, because I am in a two-dimensional complex. The link of a vertex is a graph. And I claim that for each vertex, this link is a connected graph. Okay, so that's first. So in fact, for type 3 and type 2, it's kind of obvious. Because type 2, the link is a bipartite complete graph. So any vertex of type 1 is linked to any vertex of type 3, just to give you an idea that it's really branched in all directions. And the link of a vertex of type 3, it's the same as the incidence graph in the projective plane. So you can interpret vertex of type 2 as lines, vertex of type 1 as points, and I put an edge when the point is inside the line. So for instance, this is a line, this is a line, this is the intersection point of the two lines. An hexagon corresponds in the projective space. When you have 3 lines that intersect at 3 points, it corresponds to such an hexagon. So again, the graph, the link of a vertex of type 3, it's the incidence graph of the projective plane over your field. So you have lines, you have points, and the relation, an edge, is the point is inside the line. So it's clear that it is connected. And for vertex of type 1, it's more complicated, but it's again connected. So it's it projects to a tree, which is essentially a Basser tree of in the two-dimension case. And the preimage of an edge is a bipartite graph. So again, it's very, very connected. Okay, so the links of vertices are connected. Okay, so that's an intermediate step. And after that, really the second part is that, okay, so you want to prove that it is simply connected. So you take a loop, and you would like to make an homotopy to the constant loop. So first, you have a loop in the space. You can ask for the loop to follow the one skeleton. You can follow the edges, okay, just by pushing it on the edges. After that, since all is connected, you can avoid the vertices of type 1. You can also only visit vertex of type 2 and 3. Because if you visit something of type, okay, if your loop goes like that, since the link is connected, you can go around and avoid the type 1. So you can always avoid type 1 if you want. Okay, so you have a loop passing through type 2 and 3. And for type 3 vertices, you have a notion of degree, the degree of the associated map. So the map is given up to an affine map. So up to an affine map, it doesn't change the degree. So the degree is attached to each vertex. And so maybe your loop is coming. So this is my square here, a vertex of type 3. So I have V3, V3 prime, V3 second. So type 3 is type 2, type 3, type 2, type 3. Here I have a degree, I have a degree, I have a degree. So I follow my degree function, so the loop continues. But I look at the degree, and at some point the degree is maximal. Say your base point, you put it as the identity by transitivity of the action, you can do that. So then you visit some vertices. At some point you find the highest degree. So before you were less, after you are less. So if you want, you have the function degree here. That's the way I imagine it. And Chetakov-Merev, they tell you that if you can do an elementary move to lower the degree in 2 ways, then in fact there is another one here, which is an elementary reduction of this one, which is a common one. So given a vertex where you have two ways to do an elementary reduction of the degree, there is a third one below connecting. So in fact, instead of doing the loop like that, you can avoid this one and pass here, and you do induction on degree, and that's it. Okay, so the fact that this exists is a Shestakov formula by F.
Sorry, the status, you reduce the degree?
Yeah, I reduce the maximal degree I visit for my loop. Yeah. So the existence here, it's a 50 pages proof, so it's hard, but it's just one picture, easy to picture the idea. And so I imagine here in fact, this kind of square, in fact, is like this one. It's really where I go from here to here to here. So the square is really these 8 triangles. So it's really a disk, and so I can really do a local homotopy inside this disk. So really I can. Yeah. So here you have a type 1, and you have something like that. So you really have your filled triangle, so you can really do the local homotopy here. So that's a proof of the simple, that the complex is simply connected. So if you want this Shestakov formula by F, then it was, so it's really an hard proof. So it was simplified by Kuroda around 2010, maybe a little before. And then, so okay, I was really unable to read this proof, too complicated for me, but this one I managed. So I read the simplification, and I simplified again. So I published a paper where I rewrite this proof, and my motivation was to get the result in this term, that, because Kuroda, it doesn't prove that it is simply connected, and I wanted to be sure that it's true. So I asked Kuroda, are you going to prove that? He said no, so I had to do it myself. Okay, so that's a paper in Annales de Toulouse, this one. And after that, I discussed with colleague Piotr Przytycki in Montreal, who is not at all in the field of polynomial map or variational map, but he's a specialist in combinatorial group theory. So he was really excited to have a triangle complex where there was some stuff to do, and we have a first paper with him. So I'm going to give you. So it's several theorems, and I'm going to put it just in one statement. So it's a joint with Piotr Przytycki. I guess it's a son of the complex dynamic guy. Yeah. So it's 2019. So it's result about this complex, the complex of Tame K3. So first, okay, now I know it's simply connected. The first thing we prove is that it is in fact contractible. The second one is that it's not a bounded complex, it's really infinite diameter, which is not, it should be, but it's not so obvious. The third one is that it is a delta hyperbolic. So delta hyperbolicity doesn't matter if you, since it's a notion up to stable under quasi-isometry. It's the same as saying that the triangle complex is delta hyperbolic or just the one skeleton. So the one skeleton with the obvious metric where each segment has length 1 is delta hyperbolic. So the complex is delta hyperbolic. And then the last one, there exists F inside, say, the Tame or S-Tame. You can choose Jacobian to be 1. Loxodromic WPD element. Okay, so a lot of normal subgroups because we find some loxodromic elements. As soon as you have one WP element, you have many quotients just by general machinery. And in fact, it's quite explicit, so I can give it right away. So the F has the following form. So it's G to the n H, where G is, so it's x1, x2, x3. So it's x2, x1 plus x2, x3, x3. Okay, that's my G that I put at the power n. So essentially, it's linear, but it's linear with coefficient in x3. There is a polynomial in x3. But otherwise, in x1, x2, it's linear, doesn't touch x3. And H is a 3 cycle, where you move, it's x1, x2, x3. Okay, so you have something linear, but where the coefficient of the matrix depend polynomially on x3. You do that the right number of times, say n equal 12 is okay. And you put H, and this one is going to be, so it's not a normal subgroup generated by F, which is good, it's a normal subgroup generated by F to the right power. Okay.
Sorry, Stéphane.
Yeah.
What is the second part of the idea of the proof? So you take a loop.
So I take a loop. I can avoid the type 1 vertices. So I have only type 3 and type 2. When I have type 3, I have a degree. So I have my loop starting from the identity, which is degree 1, going somewhere. And at some point, I reach the maximal degree. And when I reach the maximal degree, I have a way to, instead of going maximal degree and continue my loop, I can go to lower degree and continue my loop. So now the maximum is lower, or the number of times I reach the maximum is lower. So then it's just an easy induction. Yeah. Uh-huh. Yeah.
So part one of this new theorem
Yeah.
depends on the old theorem, depends on the simple connectivity.
Wait,
Contractor will apply simply connected, yes.
yeah, for sure.
So, but the proof of this depends on simply connected?
Well, depend on, I don't know, but. So here you want to show that any loop you can contract, and here you want to prove that there is no sphere. Because it's a two-dimensional complex, there is no embedded sphere. So it's one more information. Mm-hmm. So it's not really depend on, it's just more precise. So in fact, four statements relies on the single ID, great ID by Piotr. That we're going to do. It's going to rely on the notion of curvature. So the four results rely on the curvature trick. So let me take a sphere or disk, which is so a combinatorial a subcomplex in my complex, which is homeomorphic to a sphere or disk. So let S in my complex or D inside the complex be a combinatorial sphere or disk. Okay, so for the first one, I want to prove that there is no sphere. So it will be a proof by contradiction. Assume there is a sphere, there is a problem of curvature, contradiction. So, and for the disk, we expect that there is no, the disk should have, so they should exist, but with some constraint of the shape of the disk. Okay. So given that, we define at each vertex notion of curvature. So for each V for each vertex V inside the sphere or interior vertex. Okay, no. I try to do two definitions at the same time. It's not resolvable. For each vertex V or V in D. So you see in S it's uniform, but in D you have the interior vertices and the boundary one. So definition is going to be slightly different in the two cases. We attach a curvature. So for each vertex we define a local curvature contribution. So it's a K of V. So I do 2 pi. So I have my V. So it's part of a sphere or a disk. So I have a certain number of triangles, triangle complex, and I'm going to put some angles for each triangle. So I have to explain which angle I take. I'm going to take the sum of all the angles here, and I'm going to compare to 2 pi. So it's a classical, it's the right thing to do differential geometry. So you minus the sum of the angle over 2 pi. So that should be the definition. So if the sum is 2 pi, the curvature is 0. If the sum is less than 2 pi, the curvature should be positive. And if the sum is large, it should be a negative curvature. So, but we're going to put some correction term. So for the moment, forget about the correction term for the moment. We do the definition. After that, I will explain why we need the correction terms. OK, so we attach this curvature. And so we do that for the vertex on the sphere or vertex in the interior of the disk. And if you are on the boundary of a disk, you do the same definition, but you replace the 2 pi by pi. So here, you put pi on the boundary of the disk. Okay? And otherwise, it's the same definition. So when you do this curvature, it's natural because then you have the Gauss-Bonnet, combinatorial Gauss-Bonnet, or if you want the Euler characteristic, and you have the estimate on the sum of the curvature. So the lemma, it's a combinatorial Gauss-Bonnet. So in the case of a sphere, if you take the sum over all the vertex of the sphere of this contribution, it should be 2. And for a disk, it should be 1. The value is not really important. So the important is that it is positive. OK, so I have to define what are my angles here. So I would like, the dream will be, without any correction, this contribution is always negative or maybe 0. So if it's always 0 or negative, the sum has no chance to be 2, so there is no sphere. Okay, that's the idea of the proof. If you sum something which is at most 0 or negative, you have no chance to get 2. So if the curvature is always negative or 0, there is no sphere.
Something I don't understand. So this Gauss-Bonnet depends on the definition of K, or is you have a kind of abstract framework, so not any formula like this?
Yeah, if you I put Gauss-Bonnet because I think in terms of angle, but it's really it's a Euler characteristic formula, in fact. So it's really.
So you need some condition on the function K, you need the sum of the angles.
That's what I'm going to do. I'm going to give you the right definition of angle. Yeah, maybe. Yeah. So I have my standard triangle. So the standard one is x, y, z. The one which is here, x, y, z, x and x, y. Okay, so type 1, type 2, type 3. So around type 2, you see that here already you see a loop of length 4. So it's reasonable to put pi over 2 if you want 0 or less. You want to put right angle here, so that it's pi over 2 4 times. Okay. Around the vertex of type 3, you see an hexagon because it's an incidence graph of a projective plane. So you have a lot of hexagons. So it's reasonable to put pi over 3 again, so that it is exactly 0. And then I guess it's your question. When I have a reasonable choice for 2 of them, I have no choice for the third one. It has to be pi over 6. And we opt for the best. But it does not happen because you see that here I have 8 triangles and not 12. So pi over 6 is not right. I have a positive curvature here. And so my contribution is positive for some vertices. And so I don't have a contradiction right away. I would like to prove that the sphere is not possible. So if it was if this picture does not exist and it was only 12, the smallest number was 12, the proof will be finished. It also proves, this argument proves that there is no way to choose a shape of the triangle so that this complex is cat-0. I will come back to that, but it's not a cat-0 complex. Okay. But we're going to put some correction term so that it becomes 0 or negative everywhere. So correction terms. So I'm going to put some arrow on some edges, and then I will explain how to use this arrow to change, to correct my formula. So it's a given a disk or a sphere. We define some arrows in the following way. So it's going to be when I have 2 adjacent triangles of this form. So I have type 3, type 2, and type 0, type 1, type 2. So I have V3, V3 prime, I have V2 and V0. And I'm going to decide if I put an arrow or not here, if these 2 triangles are part of my disk or sphere. Okay. So first, in fact, on such a pair of triangles, I can put it in normal form back to my favorite one, so I can transport. I can assume that this one is a standard one. So, okay, so we can assume that this is the identity, that this one is, so maybe, yeah, okay, I'm going to put x1, x2, x3. Here it's x2, x3. Here it's just x3. And here, if you are adjacent to such a triangle, it means that it is x1 plus a polynomial in x2, x3. You apply the elementary one, and x2, x3 is here. Okay, so this is a representative of this vertex. This one is the identity vertex. Okay, so I'm going to put an arrow if the polynomial p has a special form. So if p has the following special form, so in fact it's of the form a of g of x2, x3, where a is a one variable polynomial, and g is a component of a polynomial automorphism in 2 variables. Is a component of an automorphism of K2 in the variable x2, x3. So if P is of this form, a component in x2, x3, and then application of one variable polynomial. I put an arrow, and I put an arrow in which direction? I look where I put an arrow in the direction of the vertex of type 1 encoded by G. So here I have G, x1, x2. It's a component of an automorphism of K2. So adding x3, I can see it also as a component of a Tame automorphism. So it's somewhere in my complex. And I put an arrow in the direction. If it was there, I put it there. So why is there a notion of direction? It's because when you look at all components of automorphism of K2, you get a copy of the Basser tree of this morning. And in a tree, when you have an edge and a vertex, there is a meaningful notion of direction because you are in a tree. So it's below or upstairs. I'm going to give you a few examples just to be clear. Okay, so example of that. After that, I will finish. I will explain the correction terms. So if you go like that, so you have so always you have x1, x2, x3, x2, x3, x3, and here I'm going to put x1 plus x2 square, x2, x3. Okay, so it's the square of x2. x2 is a variable. T square is a polynomial. Okay, so here a of t is t square, and g is just x2. So it fits in, and so I have to look at where is x2. x2 is somewhere here. So I put the arrow. And you see this picture, x2, x3, x2, x3. It's the picture of this morning for the Basser tree with two variables. Just like that instead of like that. If I put instead x1 plus x3 square, so now G is x3, and so x3 is here, so the arrow is like that. Okay? So the same, I just change this, and the arrow is in this direction because x3 is there. And the last one, maybe a little more complicated. So that here I put x1 plus x2 plus x3 square. Okay, so here the component is x2 plus x3 square. So here G is x2 plus x3 square, which is a component, and A is again t square. And so I have to understand where is my, so I claim it's,
How did you choose the direction? Sorry,
okay, let me do this one, and then we can discuss. So here you have, somewhere you have x2, here you have x3, here you have x3, x2 plus x3 square, and here you have x2 plus x3 square. So when I use only the variable x2 and x3, I'm putting some vertex of type 2 or 1, which are part of the Basser tree of the complex before. And so I follow until I found the x2 plus x3 square, which is what's there. So you see that you have to go there and there, so you have to go in this direction. To go from this edge to this vertex, if you go this direction, you're never going to find this one because it's a tree, so you cannot come back. No? So it's a tree, so if you want to go from the middle of the edge to here, you have to go down. And here, x2 was here, and if you want to go from here to x2, you have to go up. Okay, so that's a definition of arrow. Then, the correction term. So each time you see an arrow, so whatever, if it is a vertex type 1, 2, So if you see an arrow in some direction, you subtract P over 3 and you add P over 3. So the way we think about it is we move a contribution P over 3 from this vertex to this vertex. Subtract here, add it to it. So it's subtract, add the same quantity, so the sum is going to be the same. Okay, so that's the correction term I put here. For each arrow from this vertex, I subtract or add some pi over 3. But since each subtraction is compensated by addition, the sum is still 2, or 1 in the case of a disk. But the beauty of the rule is that now everybody is negative or 0. And so it proves that there is no sphere, because the sum cannot be 2. And for disk, it says that you cannot have too many strictly negative one, something like that. So maybe let me see what is the time? When
3 minutes left.
3 minutes left. Yeah. Okay. So I'm not going to do. What do I do? I do the last picture, just to give you an idea of the delta hyperbolicity. Okay. Okay, so the case of the sphere should be okay, and I want to comment on the delta hyperbolicity. Where? Okay, yeah. So for delta hyperbolicity, we use disks. Okay. So if you have a disk inside the complex, it cannot be like that, because we prove that the vertices with a strictly negative curvature, they fill in a uniform way the interior of the disk. So there is no big subdisk where you have only curvature 0. It's not possible. So you have many vertices where the curvature is strictly negative. So okay, my points are for strictly negative curvature. So maybe it's strictly negative, 0, 0, 0, then you have to be strictly negative again in a uniform way like that. And on the boundary, you could be strictly positive, maybe. But each time is not too much because of the formula. So you have small positive contribution along the boundary. So you see that if the number of strictly negative is, like on the picture, is quadratic, and the number of positive contribution is linear because it's on the perimeter, you're not going to find 1. You have quadratic, strictly negative, linear, positive. So this picture is impossible. And so the true picture of a disk is more like that. And the negative curvature, okay, like that. So that's my cross, if you want. And so the number of cross is with the same order that the number of points on the boundary. And this is a disk in a delta hyperbolic space. Disk look like that, even. Or at least if they look like that, it is delta hyperbolic. So you can transform this picture into a criterion for delta hyperbolicity. We understand strictly negative. In fact, we understand the flat disk, and we show that the flat disk cannot be too large. So at some point, you have to meet a strictly negative one. So that's a uniform statement. So you combine the two, and you get the delta hyperbolicity. Okay. And the two last one are, so infinite diameter is a consequence of 4. If you have a loxodromic one, it means that the geodesic is quasi-embedded, so it is an infinite diameter. So 2 is really a consequence of 4. And for loxodromic WPD, it's again an argument on using disk like that, more elaborate, but similar. Okay, so I stop here.